We are here to help.
Recognizing exact differential equations is the first step to solving them. Exact differential equations are conventionally written in a particular format in order to check for exactness. This is sometimes called standard form. M and N are multivariable functions in terms of x and y. Once we have our differential equation rearranged in this form, we can check for exactness by taking the partial derivative of m with respect to y and the partial derivative of n with respect to x, and compare them. If they are equal, then our equation is exact. Now let's look at an example that we can solve. Since this equation is already in standard form, we can easily determine what m and n are. The next step is to calculate the partial derivatives of m and n with respect to y and x respectively. The partial derivative of m with respect to y is 2x, and the partial derivative of n with respect to x is 2x. Since these partial derivatives are equal, our equation is exact. The solution for an exact equation is a function in terms of x and y, which we call phi. The partial derivatives of phi are m and n from the differential equation. We use m and n to work backwards to solve for phi. To do this, we start off by calculating the integral of m and n with respect to x and y respectively. We first integrate m with respect to x. The solution to this integral is x squared y minus 3x cubed. But because we said that the partial derivative of phi with respect to x was m, that must mean that if we take the integral of m with respect to x, we should obtain phi. But this isn't quite it. When we take the integral of m with respect to x, this doesn't exactly give us phi. If phi contained a term that's solely in terms of the variable y or a constant term, this would have gone away when taking the partial derivative with respect to x. To fix this issue, we add a term to the integral of m. In our example, the integral of m was x squared y minus 3x cubed. If we add h of y, this fixes the issue. Now we can say that this is equal to phi, and solve for h. Since the partial derivative of phi with respect to y is n, we can take the partial derivative of the equation we obtain for phi and compare it with n to solve for h prime. As we can see, h prime is equal to 2y plus 1. If we integrate both sides with respect to y, this gives us h. And we now have the final answer.